You can build a battery out of dirt for about $8, and it genuinely works. But the electricity is not coming from the soil, and it is not free. And understanding where it actually comes from is far more interesting than the version you have been told. I'm going to show you exactly how to build one, what a meter reads when you do precisely what it can and cannot power, and the honest answer to where that current originates. I'm also going to show you the part of this story that almost nobody tells, which is that this device was patented in 1841 and used to power telegraph equipment across entire countries before power stations existed. Let me start with the build, because it is genuinely as simple as it sounds. You need two pieces of metal that are different from each other, and the classic pairing is zinc and copper. For the zinc, the cheapest option is a galvanized steel nail, spike, or pipe, because galvanized simply means coated in zinc, and you can buy those at any hardware store for a few dollars. For the copper, a length of copper pipe or a solid copper ground rod works perfectly, and a thick piece of copper wire will do for a small test. Then you need two lengths of insulated wire and something to measure with, and a basic multimeter is genuinely worth owning for this. That is the entire parts list, and yes, it comes to well under $10 if you already have wire. Now you assemble it, which takes about 2 minutes. Push the zinc electrode into damp soil so that a good portion of it is buried and in firm contact with the earth. Push the copper electrode into the same soil, roughly a foot or so away from the zinc, and get it well seated so the soil is packed against it. Connect a wire to each electrode, touch your meter probes to the two wires, and read the voltage. You will see something in the region of half a volt to about 1 volt, appearing within seconds from 2 bits of metal in the ground. A few practical details make a genuine difference to that reading, and they are worth knowing before you decide the experiment failed. The soil has to be damp because a dry electrode is sitting in an insulator, so water the spot thoroughly and wait a few minutes if the ground is dry. Surface area matters more than length, since the reaction happens on the metal surface in contact with the soil, which is why a length of pipe outperforms a thin nail. Clean metal matters too, because paint, rust, and grease all get in the way of the reaction. So a quick scrub on both electrodes before you bury them is worth the 30 seconds. Spacing matters less than people expect, and somewhere around 6 inches to a couple of feet is fine. Since what you actually need is good contact rather than a particular distance, and your connections need to be solid, because a loose wire twisted around a rod will give you erratic readings and make you think the battery is failing when the fault is at your fingertips. And I want to correct something immediately, because the version of this that goes viral online often claims there is no wiring involved. That is simply false, since the whole thing is 2 electrodes connected by wires. And without those wires, you have nothing but 2 pieces of metal sitting in a garden. What is true is that there is no wiring to your house, no solar panel, no fuel, and no moving parts. Now, the meter is reading a voltage, and this is where almost everybody draws the wrong conclusion. A voltage reading feels like proof that you have found a power source, and it is not. Voltage tells you the electrical pressure available, and power requires pressure and flow together, and it is the flow that this device struggles with enormously. Put a small load across those 2 electrodes and watch what happens to the reading, because the voltage will sag immediately as soon as any current is drawn. That collapse is the single most honest thing about an earth battery, and it is the detail that every hype video leaves out. The reason is internal resistance, and soil has an enormous amount of it. For current to flow, charged particles have to physically travel through the ground between your 2 electrodes, and dirt is a poor conductor compared to the copper wire on the outside of the circuit. So the moment you ask the cell for real current, the soil itself throttles it, and the voltage you measured with no load attached turns out to be almost entirely theoretical, which is why every serious number in this video is about current rather than voltage, since the voltage is the easy part and the flow is the wall you hit. So let me tell you where the electricity is actually coming from, because this is the heart of the whole subject. It is not coming from the soil. The soil is doing one job only, which is acting as an electrolyte, meaning a medium that lets electrically charged particles move between the 2 metals. The energy itself is coming out of the zinc. Zinc is a chemically reactive metal, and when it sits in a moist, salt-containing environment while connected to a less reactive metal like copper, it begins to give up electrons and dissolve. Those liberated electrons travel out through your wire, around your circuit, and back to the copper electrode. And that flow of electrons through the wire is your electric current, which means the fuel in this battery is the zinc rod. And the battery runs for exactly as long as there is zinc left to consume. Every electron you draw out of this system is paid for with a tiny quantity of dissolved metal. That is not free energy, because it is a slow-burning battery whose fuel happens to be a hardware store nail rather than a chemical paste in a plastic cylinder. And once you understand that, the entire technology snaps into focus. Since a chemical battery from a shop works on the same principle with two carefully chosen electrodes and a purpose-made electrolyte sealed in a case, an earth battery is that same reaction, using cheap metals and whatever happens to be dissolved in your garden soil. It is not a different kind of physics, because it is a worse engineered version of the battery in your remote control, which raises an obvious and fair question, and it is the one that makes this story worth telling. If this is just a mediocre battery, why did anybody ever use it? And the answer is that for a period in the 19th century, it was genuinely one of the better options available. Let me take you back to the 1840s. And I want you to hold the right picture in your head, because there were no power stations anywhere on Earth. There was no grid, no wall socket, no generator in any ordinary building. And electricity was something you produced chemically, in a jar, on a bench. The batteries of the ERA were wet cells, meaning glass jars filled with acid and metal plates, which had to be assembled, maintained, topped up, and eventually rebuilt. And in that world, something extraordinary was happening, because the telegraph was spreading across countries and continents, and it needed continuous electrical power at stations along enormous lengths of wire. In 1841, a Scottish inventor named Alexander Bain patented an earth battery, which used metal plates buried in the ground to generate the current for telegraph apparatus. Think carefully about how attractive that was to an operator, because a buried plate needs no acid, spills nothing, and does not have to be refilled every week by a technician who has to travel to reach it. Earth batteries were used in telegraph work through the 19th century, and the idea remained interesting enough that inventors kept returning to it for decades. And there is a related piece of telegraph engineering that makes the whole era make more sense, because early operators discovered something remarkable about the ground itself. You do not need two wires to complete a circuit over a long distance, since you can run a single wire out to the distant station and use the earth itself as the return path. Both stations drive a metal rod into the ground, and the soil carries the return current across however many miles separate them, which have the amount of copper needed to wire a continent. That practice was called an earth return, and it was standard across telegraph networks, which means the ground was already understood as an electrical conductor and an active part of the system. So when someone proposed getting the power out of the ground as well as the return path, it was not an eccentric leap, because it was the obvious next thought for an engineer already burying rods at every station. In 1898, an American inventor named Nathan Stubblefield received a patent for an earth battery of his own design, and he is remembered mostly for his experiments in wireless telephony, which he demonstrated publicly before radio broadcasting existed. So this technology has a genuine, documented history in real infrastructure, and it was not a curiosity. It was a practical answer to the question of how you keep a low-power instrument running in a remote place in an age before anybody could run a cable to it. So why did it disappear? And here the answer is not remotely mysterious, because two things happened. The first is that the dry cell battery arrived, meaning a sealed, portable, standardized battery that produced far more current than any buried plate, cost very little to manufacture, and could be dropped in a pocket. The second is that power stations and the grid arrived, and once a wire ran to a building. The question of how to generate a small trickle of current on site simply stopped being a question. An earth battery was never suppressed and never hidden, because it was outclassed on every measure that mattered. And it stopped being used for the same reason nobody rides a horse to work. Which brings us to the part of this video that will save you the most money, and that is the arithmetic. Let me give you the numbers honestly, because almost nobody in this corner of the internet will. A single earth battery cell produces somewhere around half a volt to just over 1 volt, and that part sounds encouraging. The problem is the current. Since a cell in ordinary damp soil typically delivers something in the range of a few microamps up to a few milliamps, depending on soil moisture, dissolved salts, electrode size, and how far apart they sit. To multiply a volt by a milliamp, and you get a milliwatt, and a milliwatt is a genuinely tiny amount of power. To put that in context, a phone charger delivers around 5 to 10 watts, which is 5 to 10,000 milliwatts, so you would need something on the order of thousands of earth battery cells, wired together to charge a single phone at normal speed. Not 2 rods in the lawn, because thousands of pairs of rods, along with all the wire to connect them, and all the zinc to feed them. And a house is a different scale again, because an average American home runs somewhere around 20 to 30 kilowatt hours a day, which is millions of times what a pair of rods in your garden can produce. That is the honest number. And it is the reason no off-grid home anywhere is running on earth batteries. It is also the reason a $5 solar garden light with a tiny panel the size of a matchbox produces vastly more usable power than $8 of metal buried in your lawn. That comparison is worth sitting with for a second because it explains why nobody in the off-grid world uses this. A small solar panel the size of a postcard will comfortably produce a couple of watts in decent sun, which is thousands of times what a pair of buried rods delivers from a device that costs less and takes up no space in the ground. The one genuine advantage the earth battery holds is that it works at night, in cloud, and under snow, entirely indifferent to the weather. So the honest niche is not power, because it is persistence, meaning a tiny amount of electricity that simply never stops, in a place where nobody is going to visit to change a battery. So let me be direct about the claim in the title of every video like this. An earth battery will not charge your phone in any practical way. It will not power your house, or your fridge, or your lights, and it is not a survival power solution. And it is not free, because you are consuming zinc, slowly the entire time it runs. Now let me tell you what it genuinely can do, because this is where it becomes interesting rather than disappointing. An earth battery is a real, working source of very small amounts of power, indefinitely, with no sunlight and no maintenance. And there are things in that category worth having. It will light a small LED, and with the right circuit, it'll do that continuously. It will run a simple clock movement, and clocks draw remarkably little, and the most genuinely useful application is powering a small sensor. Because there is real engineering interest in devices that sit in a field or a forest and report soil moisture or temperature. For years, without anyone changing a battery, there is a technique that makes all of this far more practical. And it is worth knowing about. Instead of trying to run something directly off the trickle, you use the earth battery to slowly charge a storage device, such as a capacitor or a small rechargeable cell. The trickle fills the store over minutes or hours, and then the store discharges in a quick, useful burst, which is how a device that draws almost nothing on average can still flash an LED brightly or transmit a radio signal. Hobbyists use a small circuit for exactly this, often called a joule thief, which takes a very low voltage and boosts it up to something usable in short pulses. That combination of a trickle source and a boost circuit is genuinely clever. It genuinely works, and it is the honest version of what you can build for $8. You are not building a power plant because you are building a permanent trickle that never needs a panel or a sunny day. And if you want to make that trickle larger, the principles are the same as with any battery. Wiring cells in series adds their voltages together. So several pairs of rods connected end to end will get you from half a volt to something more workable. Wiring cells in parallel adds their current capacity, which is what you need if the problem is flow rather than pressure. Bigger electrodes with more surface area in contact with the soil deliver more current since the reaction happens at the metal surface. And moisture and dissolved salts matter enormously, which is why an earth battery in damp, mineral-rich soil noticeably outperforms one in dry sand, and why the output of a buried pair rises after rain and falls during a drought. Now let me show you the modern version of this idea, because there is genuine research happening, and it is not what most people expect. Soil microbial fuel cells work on a completely different principle, since instead of consuming a metal, they harvest electrons from the metabolism of bacteria living in the soil. Certain bacteria break down organic matter and release electrons as part of that process. And if you place electrodes correctly, you can capture a portion of that flow. That means the fuel is the organic material in the soil, rather than a zinc rod, which makes the system genuinely renewable in a way the metal version is not. The power levels are still very small, and this is still a research field rather than a product on a shelf. But it is being seriously developed for exactly the application I mentioned, which is long-life sensors in agriculture and environmental monitoring. So the honest future of getting electricity out of dirt is probably microbial rather than metallic, and it will likely power instruments rather than houses. Now, here is a detail that I think is the most satisfying thing in this entire subject, because you already own several devices that run on this exact chemistry, deliberately. The reaction that powers an earth battery is the same reaction engineers call galvanic corrosion, and industry has been using it on purpose for over a century. Look inside a domestic water heater and you will find a long metal rod called a sacrificial anode, usually made of magnesium or aluminium, hanging in the tank. Its entire job is to corrode, because by being more reactive than the steel tank around it, it gives up its own metal preferentially, and the tank does not rust. Plumbers replace those rods periodically, and the rod comes out visibly eaten away, which is precisely what happens to the zinc in your earth battery. Oats use the same trick, since blocks of zinc are bolted to hulls and outboard motors specifically so that the seawater eats the zinc rather than the propeller and the fittings. Galvanized steel is the same principle applied as a coating, because the zinc layer corrodes first and protects the steel underneath. So the chemistry in your garden battery is not obscure, and it is one of the most widely deployed protective technologies in the world. The only difference is your intention, since a plumber is trying to throw that energy away and you are trying to catch a little of it in a wire. Which brings me to the honest limits and cautions, and there are only a few. The electrical risk is essentially nil, because we are talking about a fraction of a volt, and there is no shock hazard whatsoever in a pair of rods in your lawn. The one genuine caution concerns your soil, since zinc dissolving into the ground is a real chemical process, and zinc at high concentrations is harmful to plants. A single small pair of electrodes in a corner of a lawn is not going to poison anything. But burying a large array of galvanized metal in a vegetable bed year after year is a genuinely bad idea, and I would keep any experiment well away from food-growing soil. Never connect any of this to your household wiring under any circumstances, because there is nothing useful to be gained and every reason not to, and know that your electrodes are being consumed, so the zinc will eventually thin, pit, and fail. And how quickly depends on how hard you run it and how aggressive your soil is. So let me answer the question that this whole subject really turns on, which is why the myth persists so strongly. I think there are two reasons, and both are understandable. The first is that a voltage reading is genuinely convincing, since you push two nails into the ground, touch a meter to them, and see a number appear where there was nothing before, and that feels like magic. The measurement is real. The effect is real, and the meter is not lying to you, because the only thing wrong is the conclusion people draw about scale. The second reason is that the idea is emotionally powerful, since the notion that the ground beneath us is quietly holding usable energy that somebody forgot to tell us about is exactly the kind of story people want to be true. And there is a version of it that is true, because the ground does hold energy in soil bacteria, in ground temperature that heat pumps exploit every day, and in water held at height on a hillside. But it does not arrive by pushing two nails into a lawn. And the honest version of that story is more useful than the exaggerated one, because it tells you what to actually build. Let me answer the questions I know are coming. Does an earth battery really work? Yes, and it produces a genuine measurable voltage and a small genuine current, and the only false claims are about how much. Where does the energy come from? From the oxidation of the reactive metal, meaning the zinc electrode is the fuel, and the soil is only the medium that lets the reaction proceed. Can it charge a phone? Not in any practical sense, because the power available is roughly a milliwatt per cell against the several watts a charger needs. How long does it last? For as long as there is zinc left to consume, which for a light load and a substantial electrode can be a long time, and for a heavy load is much shorter. What can it actually run? A small LED, a clock, and most usefully a low-draw sensor, especially when paired with a capacitor and a boost circuit that stores the trickle and releases it in bursts. Does it work better in wet soil? Considerably, since moisture and dissolved salts carry the ionic current, so output rises after rain and drops in drought. Is it safe? Electrically, yes, and the only real caution is avoiding zinc accumulation in soil where you grow food. Is this the same as a lemon battery? Essentially, yes, Because a lemon battery is two dissimilar metals in an acidic electrolyte, and an earth battery is two dissimilar metals in a soil electrolyte. So here's the whole of it. You can build a working battery for about $8 using a galvanized nail, a piece of copper, and the ground outside your door. And a meter will confirm within seconds that it is producing electricity. The current is real, and the physics is genuine. And the energy is coming from the slow chemical consumption of the zinc rather than from the earth itself. Which means it is a battery with a hardware store nail for fuel. This exact technology was patented in 1841 and used to power telegraph equipment across the 19th century, when there was no grid and no better option, and it was retired not by suppression, but by the dry cell and the power station. The output is around 1 milliwatt per cell, which will light an LED and run a sensor for years and will never charge a phone or power a house. And the same reaction is hanging inside your water heater right now, bolted to the hull of every boat in your local marina, and coating every galvanized nail in your shed, because industry has been deliberately using it to protect steel for over a century. So tell me, down in the comments, whether you have ever actually built one of these and measured it, and what your meter read. And if you have run a sensor or a light off one for any length of time, tell me how you did it, because that is the version of this project that genuinely works, and I would like to see it. I read every single one. Next time, I'm going to show you the machine that moves water uphill continuously, day and night, using no electricity, no fuel, and no solar panel. Invented over 200 years ago and still running on farms today. Subscribe so you don't miss it. And remember that the honest version of a technology is almost always more useful than the exciting one.